Let us start with 7.2, generating functions. 7.2, generating functions. And so what is a generating function? Okay. So generating function is a function that corresponds to a sequence. So given a sequence of real numbers, a n, where n goes from, as usual, 0 to infinity, the corresponding generating function is a function whose coefficients of x to the n is a n, is equal to summation n is equal to 0 to infinity a n x to the n. Okay, where x is your normal variable, and we don't really care if the sum converges or not. We will bother about the convergence later on. Formal sum. Don't worry about convergence. Don't worry about convergence. Okay, so this is what a generating function is. Okay, and oftentimes to study a sequence, it is easier to look at this function and look at its properties, because functions oftentimes are quite easy to study compared to trying to figure out the 1000th coefficient by looking at the entire sequence. I can just look at the function, see how it behaves, and that might give me a better idea. For example, let my sequence n is equal to 1, equals 1 for every n. Then what does my generating function look like? Well, my gx is equal to summation n is equal to 0 to infinity 1 times x to the n, which is just summation n is equal to 0 to infinity x to the n, and this I know is just 1 over 1 minus x, right? So if I want to look at this sequence, I can just look at its generating function, which is relatively easy. Similarly, if I want, suppose my n is 1 over n factorial for every n greater than or equal to 0, then my g of x is equal to summation n is equal to 0 to infinity x to the n over n factorial, which some of you might know is actually the Fourier expansion of, not Fourier expansion, the expansion power series of e to the x. You might have seen this in calculus before. This sum need not always be infinite. It could also be a finite sequence. So, example, suppose I have a finite sequence. Consider the sequence a n is equal to m choose n, right? Find the generating function. Find the generating function. Then answer. n is equal to 0 for every n greater than or equal to m. Oops, not greater than or equal to, strictly greater than m, right? So I am only looking at m is equal to, so I'm only looking at m choose 0, m choose 1, all the way up to m choose m. And later on, it's all zeros. and my generating function g of x is going to be summation n is equal to 0 to m choose n x to the n, which by now you should be familiar with, and you should be able to recognize this as exactly 1 plus x to the power m. Okay, let's do another example. Suppose an is the number of integral solutions integral solutions to e1 to ek is equal to e1 plus e2 plus dot 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 plus ek is exactly equal to n, where even to ek are integers all greater than or equal to 0, where e1 dot 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 ek belong to integers greater than or equal to 0. So I don't remember if I have defined this symbol in class or not. Hopefully I have. This is integers, which comes from the German for integers, which is, I think, Zahl. So we don't want to use I for integers, we use Z. Okay, I want to find the generating function. Answer. Well, I know that an is going to be, well, n plus k minus 1, choose k minus 1 by my by the dividing thing method. You have seen this before multiple times, which is also equal to n plus k minus 1, choose n, right? And so this is equal to my g of x is equal to summation n is equal to 0 to infinity a n x to the n, which is equal to summation n is equal to 0 to infinity n plus k minus 1, choose n x to the n. Now, just keep in mind, this sum, unlike the previous one, is not finite. Unlike the previous one, this is not a finite sum, but you have seen this sum before. This was our expansion in the Newton's binomial theorem of 1 minus x to the minus k, right? By Newton's binomial theorem. Okay, so these are a few examples of generating functions. We can look at this exact same one another way. If I wanted to look at it, I could have said that, recall that we used 1 over 1 minus x is equal to summation n is equal to 0 to infinity of x to the n. That was just a couple examples before, right? Is equal to summation n is equal to 0 to infinity x to the e is equal to 0 to infinity x to the e. And why am I writing it as e? Because I want to write, so 1 over 1 minus 1 minus x to the power k is equal to 1 over 1 minus x times 1 over 1 minus x times 1 over dot 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 1 over 1 minus x. They're exactly k of these, k times, and I'm going to write each one of these as a different e. So this is equal to summation e1 is equal to 0 to infinity x to the e1 times summation e1 is equal to 0 to infinity x to the e2 dot 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 summation ek is equal to 0 to infinity x to the ek. Well, the product of this is a gigantic sum where e1 is equal to 0 to infinity, e2 is equal to 0 to infinity, dot 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 summation ek goes from 0 to infinity. It's a k sum of k things, right? X e1 plus e2 dot 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 plus ek. But this is exactly the same sum as just instead of summing over e1 to en, I could just sum over the total power, n is equal to 0 to infinity. And then the coefficient is how many ways are there of writing, number of ways of writing, n is equal to e1 plus ek. Okay, x to the n with e1 to ek greater than or equal to 0. And that was exactly my original n is equal to 0 to infinity a of n x to n, and hence this is my generating function g of x. Okay, so let me let's do one more example. Okay, so now I have this for exactly equal to for e1 to en are greater than or equal to 0. I can ask the same question but say, oh, I don't want them greater than or equal to 0. Can I do some more things? Can I say that, oh, some of them have to be greater than 4, some of them have to be some other things? So let us say that example an is equal to number of integral solutions to, let's say, let me restrict to e1 plus e2 plus e3 plus e4 is equal to n. So not too many more. Okay, let me just take 4 of those. I'm also going to take e1, e2, e3, e4. For convenience, I'm going to take them greater than or equal to 0, but with the extra condition that e1 even, e2 is odd, e3 is actually smaller than or equal to 4, and e4 is greater than or equal to 1, not just 0. It has to be greater than or equal to 1. Now I want to find the generating function. Find generating function. Okay, I am going to use the second method that I used before. G of x is equal to summation n is equal to 0 to infinity a n x to the n, but this is also going to be, well, summation e1 is equal to 0 to infinity x to the e1 even multiplied by summation e1 is equal to 0 to infinity, e2 is equal to 0 to infinity x to e2, with the extra condition that e2 is odd. x3 is summation e3 is equal to 0 to infinity, not 0 to infinity, my bad, 0 to only 4 because E3 needs to be smaller than or equal to 4. X to the E3 and E4 is equal to 1 to infinity x to the E4. Right? Then let me write this down. What does this sum look like? Well, it does not start with 0. Sorry, it does start with 0. 0 is even, so 1 plus, I don't have x, I have x squared, plus x to the 4 plus dot 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 multiplied by, now this one does not start with x to the 0. It starts from x to the 1 plus x cube plus x to the 5 plus dot dot dot. This one is just 1 plus x squared plus x cubed plus x to the 4. And this is equal to x plus x squared plus x cubed plus dot dot dot. Right? Now, what I can do is say, hey, I know these are power series, right? I can write this as 1 over 1 minus x squared. This is exactly the same expansion. This is equal to, 1 over 1 minus x squared. This is exactly this thing multiplied by x, right? If I multiply all of this times x, I just get this series, right? So that's 1 over x to the 1 over 1 minus x squared times x. This is equal to 1 minus x to the 5 over 1 minus x. And this is equal to 1 over 1 minus x multiplied by x. And so, without having to actually compute all of this multiplication and whatever horrible mess I would have gotten into, I can safely say, oh, the generating function that I'm going to get is 1 over 1 minus x squared times 1 minus x squared times 1 times 1 times 1 minus x to the 5 times x. Sorry, 1 times x times 1 minus 5 to the x, 1 minus x to the 5 times x, which is equal to x squared times 1 minus x to the 5 all the way over 1 minus x squared times 1 minus x squared. Okay, let me stop this one here.